Production has been pushed faster than anything ever ramped up in industrial history. When you look purely at speed and scale, setting aside debates about panel gaps or early build quality for just a moment, Tesla operates in a category of its own. The company doesn't just set production records. It establishes a new benchmark and then breaks it again in a remarkably short span of time. Every production line is continuously refined, optimized, shortened, and re-engineered until there is almost no time left to cut. Elon Musk has even gone on record stating that Tesla could eventually build a standard vehicle in under 5 seconds. Imagine that for a moment. A full-sized road-legal car coming off the assembly line faster than most people can tie their shoes. It sounds unrealistic, almost absurd, yet that is exactly the direction Tesla has been heading. What once sounded like a futuristic exaggeration has now become reality. Tesla has officially surpassed its own milestone, developing a production system capable of completing a vehicle in just 4.5 seconds. That is half a second faster than its previous record. And at that speed, the process is so fast that the human eye struggles to follow what is happening. The line moves with a blur of mechanical precision as fast and sudden as a lightning strike. You cannot stand close to it. In fact, safety constraints mean people physically cannot approach the line while it is operating at full speed. One moment nothing is there, and the next, a completed car exists. You are left asking yourself how it even happened. The real question is not just how fast Tesla can build a car, but how such a system was even designed in the first place. This production technology completely rewrites the traditional rules of car manufacturing, and it places Tesla years ahead of its competitors. Most legacy automakers would need more than a decade to design, test, and deploy anything remotely comparable. This is not incremental improvement. It is a structural leap, and the implications extend far beyond a single factory or a single vehicle. To understand how radical a 4.5-second build time really is, it helps to compare it with something familiar. An automatic espresso machine typically takes between 30 and 60 seconds to brew 1 cup of coffee. While you are waiting for that coffee, at least 6 fully built Tesla vehicles can roll off the production line. Not shells, not half-finished frames, but complete, drivable cars. And these are not premium flagship models. These vehicles are expected to be the Tesla Model 2, the company's most affordable car yet. The Model 2 is scheduled to debut early next year, with production volumes rumored to be roughly double that of the Model Y. Pricing estimates place it
somewhere between $20,000 and $30,000.
with Elon Musk himself suggesting that the cost of production could be around $20,000 per unit. That price point alone would already make the model to one of the most disruptive vehicles ever introduced. Combine that with a production system capable of outputting cars in under 5 seconds, and you begin to see why this model is expected to sell at an unprecedented scale. Whenever a new car is announced, most people focus on design, driving range, acceleration, interior features, or infotainment screens. Rarely does anyone stop to think about where that car is built and how it is actually made. Normally, it doesn't matter. But when a vehicle is being produced in 4.5 seconds, the manufacturing process itself becomes impossible to ignore. At that speed, skepticism naturally arises. Is quality being sacrificed? Can a budget-friendly vehicle built this fast really meet safety and durability standards? These are valid questions, and answering them requires looking inside Tesla's global manufacturing network. Today, Tesla operates 5 major factories directly involved in vehicle production. Each plays a specialized role within the company's ecosystem. In Europe, Gigafactory Berlin-Brandenburg focuses primarily on building the Model Y for the European market. In China, Gigafactory Shanghai produces both the Model 3 and Model Y, and currently holds the highest production capacity in Tesla's global network. Its efficiency and scale have made it a benchmark factory even by Tesla's own standards. In the United States, Tesla's Fremont factory remains one of the most versatile facilities, producing the Model S, Model X, Model 3, and Model Y despite being housed in a facility originally designed decades ago for traditional auto manufacturing. Fremont has been continuously upgraded and optimized to support Tesla's rapid production philosophy. Then there is Giga Nevada, which is responsible for producing the Tesla Semi. The Semi is one of the most challenging vehicles Tesla builds due to its massive size, heavy-duty performance requirements, and complex manufacturing demands. Even so, Tesla remains confident it can eventually reach an annual output of around 50,000 units. Finally, there is Gigafactory Texas in Austin, the focal point of this entire story. Giga Texas is currently producing the Cybertruck and the Cybercab, and it is widely expected to become the primary production hub for the upcoming Model 2. This factory represents Tesla's most advanced vision of what vehicle manufacturing can become. Inside, you will see very few humans working near the production line. That is not because people are unnecessary, but because most tasks are handled by robotic arms, massive gigacasting machines, and fully automated systems operating around the clock. These machines run 24 hours a day with minimal downtime. The environment feels less like a traditional car factory and more like a high-tech laboratory. It is not an exaggeration to say that the production line at Giga Texas looks like Tesla is building advanced toys at industrial scale. Each vehicle rolls out almost the same way Matchbox cars are made, except the process is magnified to real-world proportions and guided by artificial intelligence, precision robotics, and advanced materials science. The speed is so extreme that at first glance, it feels unreal, almost like watching an AI-generated science fiction sequence. But every bit of it is real. Everywhere you look inside the factory, you see evidence of how aggressively Tesla has optimized the process of building a car. Conveyors move seamlessly. Robots operate with choreographed precision. Entire sections of the vehicle appear and lock into place in moments. At the heart of this speed lies one critical component of the production line: the body panels and structural frame. This has always been the most complex and time-consuming stage of vehicle assembly. Traditionally, automakers relied on massive stamping presses where flat sheets of metal were placed between dies and pressed into shape. Each panel required multiple steps, multiple machines, and extensive welding to assemble into a complete frame. That entire approach is now effectively obsolete within Tesla's most advanced factories. Tesla has replaced stamping with something far more radical. Enter the Gigapress. This machine is widely regarded as the most powerful and transformative piece of equipment in Tesla's entire production system. Elon Musk once described it as a Matchbox car-making machine scaled up to real life, and that analogy is surprisingly accurate. Instead of assembling dozens or hundreds of individual metal parts, the Gigapress casts massive sections of the vehicle in a single shot. The idea itself was simple but revolutionary. If you can injection mold plastic toys as single pieces, why not apply the same logic to cars using metal? The result is an engineering giant, a high-pressure die casting machine capable of delivering up to 50,000 tons of clamping force. This level of power allows Tesla to form entire structural sections of a vehicle in seconds. For the Model 2, the Gigapress is expected to cast the rear underbody in roughly 3 seconds. What makes this approach so disruptive is how completely it breaks the logic of traditional car manufacturing. In older designs, even within Tesla's own lineup, the rear body of a vehicle like the Model Y was assembled from around 70 separate components. Each part had to be stamped, aligned, welded, inspected, and integrated. That process required hundreds of welds and an extremely complex robotic system, just to bring everything together. By switching to gigacasting, Tesla was able to replace those dozens of components with just 2 large castings and a structural battery pack. The result was not only faster production, but also massive cost savings. Manufacturing costs were reduced by as much as 40%, while structural rigidity improved, and overall complexity dropped dramatically. Fewer parts mean fewer points of failure, simpler logistics, faster assembly. For the upcoming affordable vehicle platform, Tesla is pushing this concept even further. The Model 2 is expected to be smaller than the Model 3, with very short front and rear overhangs and a simplified structural layout optimized for gigacasting from the ground up. This is not a scaled-down version of an existing car. It is a vehicle designed specifically to be manufactured at unprecedented speed, Every aspect of the Model 2's design feeds into this goal. The wiring architecture is simplified. The interior layout minimizes part count. The structural battery pack doubles as a load-bearing element, eliminating redundant components. Even paint processes are optimized to reduce time and material usage. All of this contributes to a system where speed does not automatically mean lower quality, but rather higher consistency. One of the most misunderstood aspects of high-most speed automation is the assumption that faster always means sloppier. In reality, the opposite is often true. Robots operating in controlled environments can repeat the same action with microscopic precision millions of times without fatigue. Huma